Okay, for this problem, we're going to investigate an actual baseball pitch using some real numbers from baseball. So in this case, we have a pitcher releasing a baseball 2 meters above the ground, and we want the ball to go into the catcher's mitt, where the catcher's holding the mitt about 0.9 meters above the ground. And the distance from the pitcher's release point to where the catcher catches it is 17.4 meters. I've chosen 90 miles per hour, which is about 40.2 meters per second, as the pitch speed. And so we're going to see if this works. Does the pitcher throw the ball straight? Does the pitcher throw the ball up a little bit? Or does the pitcher throw the ball down a little bit in order to hit the mitt? So let's erase this text here so we have room to write. So we can figure out how to solve this problem. We can figure out by looking at the horizontal trajectory. Because if the pitcher throws the ball completely horizontally and it arrives too high or too low, that will tell us whether the pitcher needs to throw the ball up or down. And since that's the simplest mathematical case to use, let's start there. So we know how fast the ball is traveling initially in the x direction, and that's the reason why we pick the horizontal trajectory, because then our initial velocity will just be in the x direction. We can use that to figure out how long it takes the ball to travel that 17.4 meters sideways. And then once we know how long that takes, we can figure out how far the ball drops away from the horizontal trajectory in that time. And so pictorially, that looks like this. So we have an initial velocity that's going sideways. That's all going to be in the x direction. And so that ball is going to travel sideways the 17.4 meters. But what's really happening, of course, is that it's falling away from this trajectory a little bit. And so this distance here, which we'll calculate, which will be the change in height of the ball, will tell us whether or not we hit the mitt or whether we were too high or too low. And so that's what we're going to do. OK, so we have then our x position is going to be equal to the initial x position plus v initial x times time. And we want to end up, so we're starting at a release point, let's call the initial point 0. And so the initial point is going to be 0. And then I have my 40.2 meters per second times the time it takes to travel all the way across. And we want this to equal 17.4 meters, which is the total distance that we need to travel. And so you can see that this is very simple. I can solve for time. So the time it takes to travel over that distance is going to be equal to 17.4 divided by 40.2. And so that's going to be equal to 0.43 seconds. So you can see that a batter really has to have pretty quick reflexes because it takes less than half a second for the ball to arrive at the plate. OK, so in that 43 seconds, we can figure out then how far the ball falls in that time. And so we know that we can write our final y position is going to be equal to our initial y position plus v initial y times time, but that term is equal to 0. So then we just have minus 1/2 times g times t squared. And this time is the time that we just solved for the total time that it takes the ball to go sideways. OK, and so my initial y position is 2 meters. And so I can plug in 2 meters here, minus 1/2 times g times my time squared. So that's 0.43 seconds squared. And so if we put in numbers for that, we find that the ball, the final position of the ball, when it reaches that 17.4 meters, is 1.09 meters. And so what that tells us is that since we wanted the ball to end up at 0.9 meters, not 1.09, this tells us that if the pitcher throws the ball straight across and just allows it to fall away from the straight line, that it misses the catcher's mitt. It's about 20 centimeters too high. So we have to throw the ball down a little bit in order to hit the mitt. And so the extra distance that the fall is needed is, so we need an extra delta y of about 0.19 or 0.2 meters. And so without changing things too much, we can kind of approximate what component of y velocity we need to generate this extra downward motion. And so we know that the ball travels for about 0.4 seconds. And so in 0.4 seconds, we want the ball to travel an extra distance down 0.19 meters. And so we can sort of separate the horizontal and vertical motions here. This is just an approximation, but it's not going to change the answer too much. And so we can say that minus v initial y times my 0.4 seconds is going to be equal to my minus 0.19 meters. And so my initial y velocity is going to have to be equal to about 4.6 meters per second in the downward direction. And so if we then look and see how we can relate that to my initial x velocity, so I'm going to add a little extra y component here, downward. So this will be my v initial y. And so we can figure out the angle with which I have to throw the ball. And so the tangent of that angle is going to be equal to v initial y over v initial x. And again, this is an approximation, but it gives us a kind of order of magnitude feel for it. And so this is equal to 4.6 meters per second divided by 40.2 meters per second. And so if I take the inverse tangent of this ratio, I get that theta is approximately equal to 6 degrees. So if the pitcher throws the ball slightly downward, 6 degrees is not a very big angle, then the ball will hit the catcher's net.